So we just finished the lab analyzing a sample of copper oxide. We're going to run through a series of calculations here that will let us determine the formula of the copper oxide. You will want a calculator and a piece of paper, maybe even a periodic table from the back of your textbook would be fantastic. Notebook would be great. It could just be a regular piece of scratch paper. And as we go, you will write down all these calculations on your paper and then take a picture, upload that photo of your work into the Canvas quiz, and then it's game over. Eventually, when we take the summative on this unit and a couple of the next few units, when the questions become a little more of a calculation, the questions in the quiz will ask you to do the same. Take a photo of your work, you'll kind of do the calculation on paper, and then you'll upload a photo into Canvas. So this will be kind of a good practice. All right, so on your paper, let's first start by summarizing the data that we collected. Okay, so here's the data. First thing I measured was 2.50 grams of copper oxide. All right, so then we did a chemical reaction. We added some hydrochloric acid and some zinc. And after this chemical reaction, the oxygen was let go from the copper, so that eventually I was left with copper metal. I collected the copper metal on a piece of filter paper and then let it dry. So the mass of the filter paper was 0.98 grams. So we masked the filter paper alone, and then after the copper and filter paper were dried, I masked them again and got a mass of 2.95 grams. So that was copper plus filter paper. All right, so I think we kind of mentioned in the lab video that if this would have been something like magnesium oxide, well, then I wouldn't have needed to go through any of this process to determine the formula. I know that magnesium is always +2, oxygen is always -2, MgO, there's my formula. But often it's a little different situation when you have a transition metal because they can have different charges. In the lab, I have 2 different containers of copper oxide. One of them is copper +1 oxide, and the other is a copper +2 oxide. And so with it being copper +1, I would have to balance that or crisscross the charges, and it would have been like Cu2O, so that I had a +2 and a -2. If the copper is +2, then it's neutral, just kind of like magnesium oxide, +2, -2. So I kind of know one of the 2 formulas should match my data. It should either be this guy, Cu2O, or this guy, CuO. It should either be a 2-to-1 or a 1-to-1 ratio of copper to oxygen, just because +1 and +2 are the most common charges on copper, and those are the 2 containers that I have. Okay, so there's one other piece of data that I kind of like to list, and that is the mass of the copper alone. And so to get the mass of copper alone, all we have to do is a little subtraction. I know the mass of the copper plus the filter paper, so would it make sense if I took the 2.95 grams and subtract off the filter paper? Then the difference should be the amount of copper that I collected. So this would have been the copper plus, what if I call it FP, filter paper, and I just subtract off the filter paper. The other piece of data that I'd really like to have recorded is just the amount of copper that I would have collected. All right, so 2.95 minus 0.98 is about 1.97 grams of copper. Awesome. Okay, and that's why it was nice to mask the filter paper alone, because it's kind of hard to like scrape all the copper off of the filter paper and just mass it. That there's usually a little bit of copper that kind of sticks to the paper. Now I don't even need to worry about it. All right, so here is my data. Eventually now, I want to figure out the formula of this copper oxide. So I want to know how many atoms of copper to how many atoms of oxygen. What is the ratio? Well, we always kind of said that a unit that gives me a ratio of atoms is the mole. And so we've had some data like this given to us in the textbook, and now we just collected the data ourselves. So let's see if we can analyze this sample. So first thing I want to do now is determine the mass of oxygen. So this is going to be the mass of oxygen released. There we go. So the oxygen was separated from the copper, but being a gas, it just kind of went off into the atmosphere, and I didn't physically collect it. I only collected the solid. But just like some of the sample problems in the book, we can figure out how much oxygen would have been released. And so I take my original sample. I started with 2.5 grams of copper oxide. And then if I just subtract the amount of copper remaining, that was the 1.97 grams. The difference is the oxygen released, right? Like, that makes sense. So we subtract 2.5 minus 1.97. Whoopsies. 2.5 minus 1.97 gives me about 0.53 grams of oxygen. Awesome. Okay, so now we've got the mass of copper and we've got the mass of oxygen in the original sample. Mass of copper, mass of oxygen. The problem is, in a formula, that ratio of atoms is not a ratio of grams. A unit that measures a quantity of atoms would be the mole. But if I have grams, I could easily convert grams to moles. So we're going to do a little calculation. Okay, so now I'm going to set up a calculation to get moles of each element. We're going to convert grams to moles. All right, so this isn't bad. I take my grams of each, 1.97 grams of copper, and then I just had 0.53 grams of oxygen. And then we'll just convert those grams into moles. So I'll set up a proportion. We want to cancel grams. We want moles, a unit that represents a quantity of particles. On my periodic table, 1 mole is about 63.546 grams. And for the oxygen, we'll set up the same type of calculation. Get it out of grams, so I want that on the bottom. It'll cancel. I want moles on the top. And my periodic table says 15.999. All right, so for each, we'll just divide. 1.97 divided by 63.546. When you get to this point, I mean, you're probably going to have some kind of wacky numbers. I would just suggest leaving a few decimal spots. Maybe like at least 2 or 3 decimal spots. Like here, I think I'm going to go 0.031. And that would be moles of copper. Then we're going to do the same thing with the oxygen. 0.53 divided by 15.999. And I get about 0.033 moles of oxygen. Awesome. Okay, so now we're just rolling with it. This is just like how we calculated any empirical formula. Once we have moles, fantastic. We want a whole number ratio of moles to become then my little subscripts in the formula. Well, these aren't whole numbers, they're really tiny numbers. So I think what I'm going to do now is divide by the smallest moles to obtain a whole number ratio. Okay, so I have an idea what this is going to be. I mean, obviously, they're kind of close to being the same, right? This one's a little bit smaller. So maybe 0.031, and we'll divide by 0.031. I know this is going to give me a 1. It's going to be darn close, right? Divided by 0.031 gives me 1.0686, blah, blah, blah. Well, guess what? That is close enough to a whole number, especially when we're working with real lab data. There's going to be some error in my original measurements. Did I conduct the experiment perfectly? I mean, I tried to do my best, but did I fully react the copper? Did I fully collect the copper out of the beaker? Did I filter it properly? Lab measurements might not always give you perfect ratios, but to be honest with you, this is pretty darn good. I am okay with this ratio. And so now we can write an empirical formula. We've got our simple mole ratio. Awesome. So I'm going to say then that this will be like my next heading. Determine the empirical formula. And it's going to be a piece of cake because I just determined my simple whole number ratio to be really close to 1 to 1. I'm going to say C, whoa, that's a weird C, C-U-O. I did it again. Good night. C-U-O. Which then, if I wanted to go backwards and say, okay, well, what's the name of this thing? Because technically, copper should have a Roman numeral with it being a transition metal. Well, I know oxygen is always a -2. So if I determine that it was a 1 to 1 mole ratio, then I can also say that the copper must have been +2. This was copper 2 oxide. And it really was. So I really do have 2 bottles of copper oxide, and it really is these two. I have a copper 1 oxide and a copper 2 oxide. And I really did pick the copper 2 oxide. So our data is pretty darn close. I am not hating this. I like it. Okay, so now here's where maybe we'll go for an extension. We got this formula. Let's check and see if my data was spot on. I mean, it was pretty close. But maybe we can figure out where our errors may lie. So what if I did this for my next question? What if I had something that looked like this? Calculate the theoretical percent copper in copper oxide. And now I know the formula. So what if we did all this work with our lab data, but now we want to confirm that it was good? I mean, I know that that is the version of copper oxide that I picked, and so I am not mad at my data. But what if I wanted to confirm or see, did I make any errors along the way? Let's see how good the data was. Calculate the theoretical percent copper in copper oxide. Theoretical means no error. Theoretical means periodic table. That we're going to use masses from the periodic table because there is no flaw or error in those molar masses. There's some flaw in these numbers, in these masses. Those are my lab measurements. And so if I spilled a little copper or I didn't fully react to the copper, those numbers might not be perfect. And obviously I didn't have a perfect 1-to-1 ratio. It's obviously close. But let's see where our errors may lie. So theoretical means like this is the true accepted percent copper. All right, so we're going to use my periodic table to say percent copper. Well, it's a 1-to-1 ratio, so 1 copper, 63.54, 6 grams of copper, divided by the molar mass of copper oxide. So I'm just going to take that 63.546 and add an oxygen, 15.999. So I get a molar mass of about 79.545 grams of copper oxide. Multiply by 100 to get a percent. Let's see what we should be looking at. 63.546 divided by 79.545 times 100 leaves me at about 79 point, oh brother, I'm going to say 89% copper. What I kind of like about this series of calculations that we're running through is that it's a really good review of a lot of the concepts in this unit. We've had to do some mole calculations. Now we're doing a percent composition. We're going to use this percent composition in a second. We reviewed the empirical formula stuff. It's really good. Okay, so yeah, I got my empirical formula. I've got my theoretical percent copper. Now here's what I want to do with that. I want to calculate, oopsies, gosh, I can't spell today. I want to calculate the mass of copper in 2.5 grams of copper oxide. How many grams of copper should have been in my original sample of copper oxide? I started with about 2.5 grams of this black copper oxide. How much copper should have been in that sample? That's why we can take our theoretical percentage, that's this guy, 79.89% of the mass in copper oxide should be copper. That's true of any sample of copper oxide. This version of copper oxide should be 79.89% copper by mass. So let's take that percentage as a decimal, 0.7989, and then we'll multiply it by our sample size. So then it's kind of like saying about 79% of that 2.5 gram sample should have been copper. Oh my gosh, let's see what we get. 0.7989 times 2.50. Yeah, it's not bad. So if we leave maybe like 2 decimal spots, because that's kind of like my other mass, it's like right at 2. Okay, so it's 2 grams of copper that should have been in my original sample. And so here's what we can kind of do now at the end of our lab to just check our data and see, like, was our data good, or where might our errors lie? It's like saying 2 grams is what I should have collected. I should have collected. I mean, based on like theoretical percentages, any sample of CuO should be about 79% copper by mass. So 79% of my original sample should have been copper. So I should have had about 2 grams of copper. Now if we go all the way back to my data, here's what I actually collected. I mean, it's really close. I actually collected about 1.79 grams. Ah, okay, so here's the comparison. I'm going to say 1.97 grams of copper is what I actually collected. Amount I actually collected. And from here, it lets us examine our errors a little bit. So the amount of copper that I collected was a little bit low. And again, it's really close. This is fantastic data. But what if somebody wanted to ask you then, if you could run this lab again, what might you do differently? Obviously, I lost a little bit of copper. I'll leave it in orange. My error, I lost a small amount of copper. I was supposed to get 2 grams, I had 1.97. Obviously, again, it's really close. But where might that copper have gone? Well, one of the most common errors is completely washing it out of the little beaker. I rinsed it about 3 times. So, and you get all this solid copper that kind of sticks to the bottom of your beaker, and you're trying to get it all out into that funnel with the filter paper. And you add more water and you kind of swirl it around, and then you send it back into the funnel. And I think I did that about 3 times, but sometimes there's just a little bit of copper that still kind of sticks on the sides of the beaker. Maybe I should have rinsed my beaker a 4th time. And in the end, all that extra water is fine. We just dumped it down the drain. So yeah, maybe I didn't get all the copper out of the beaker. I should have rinsed it a little bit better. Sometimes you have to be careful that like you don't poke a little hole in your filter paper. And if you poke a hole in your filter paper, some of that copper might like drip through into your flask. And so we wouldn't want to do that. We want to make sure that all the copper then stays on that paper. Sometimes kids too like to kind of take their stirring rod and like poke at it a little bit. And they poke at it, but they don't realize that then some of the copper sticks to their stirring rod. And so then that's another way too that you would have lost a little bit. Again, it's not much, but it does end up kind of affecting your final results. So a fantastic set of real lab measurements that let us run through the types of calculations that were shown in the book. But now we were just able to kind of see the reaction that would have led to those measurements. And so in the end now, all you have to do is take a photo of the work that you just wrote in a notebook or on some scratch paper, and then you'll upload that into Canvas. But I would also suggest just hang on to this work, because in the end, if there's something similar on a summative, now you've just got an extra practice problem to kind of look at as another example.